These frogs are home to South Africa, particularly Madagascar, where they're secluded and have a really nice high success rate and high diversity, and Central South America, as we can see in the second picture, where you can see the higher frequency of these frogs shown in the Amazonian area, where they are undisturbed as well. They're all part of the family Dendrobatidae, and these frogs all secrete poison through this mucus-like skin. And their morphology uses saltatorial movement, so they use jumping movement. Saltatory means jumping, and this is done by using a hind limb extensor mechanism that propels the frog into the air. And this is what gives them their distance, their height, and their really fast propulsion. And some recent research has shown that there's a lot of cranial morphological variation between poison frog species, and this looks like it's more based on location. So frogs that are in the Central and South American region have different cranial morphological features compared to the South African frogs and Madagascar frogs. And this is probably due to differences in prey and predators and detection of these different prey and predators that use different mechanisms in their brain and need different muscle arrangements to accomplish this. As said before, these frogs are poisonous, not venomous. So you can see in this first figure, if you bite a frog, it will kill you, but snakes bite you and kill you, so that's the difference, being bitten or biting. And then, as you can see in the second picture, these frogs are even used for hunting. So what they do is they take the poisonous mucus layer and coat their darts with this from the frogs, the poor frogs, and blow darts at their victims and use it to cause sweating, nausea, paralysis, and even death in extreme cases. These are the symptoms of poison. In addition to these, the frogs also have their vibrant coloration, which is also used to deter predators.
Hi, I'm Victoria, and I'm going to be going over the diet of the frogs as well as the toxin. So for the diet, their diet consists of ants, termites, beetles, fruit flies, and millipedes, depending on the species. Ants seem to be the most common source of food seen throughout species. Poison frogs receive alkaloids, which make up toxins from their diet. An interesting fact is that poison frogs collect and store toxins from their prey in their skin instead of creating it. Toxin levels can change depending on the access to their native food sources. It's even possible to have a poisonous frog that isn't poisonous because they are not fed their native diet. There are currently 800 different types of alkaloids found in poisonous frog species today. The main one being batrotoxin, which is found in most poisonous frogs. They avoid self-poisoning actually by having a mutation that allows them to resist this specific toxin.
I'm Maddie, and I'm going to be going over the functional and evolutionary story of these frogs. Poison frogs are members of the family Dendrobatidae, which consists of 16 genera of poison frogs, and as previously stated, they're native to Central and South America as well as Madagascar. Most of the individuals in this family are distinguished by their phenotypic variation identification. And phenotypic variation is the genetic expression of a gene. So for example, if your mom has blue eyes and your dad has brown eyes, their eye color will be the phenotypic expression of genes that code the eye colors. So these species are primarily identified by their extravagant colors, their limb length and ratios, size, and location. Most animals use their coloration to blend into their surroundings, but these frogs do not. And as you can see, they don't exactly blend well into the leaf litter that is commonly found in their environments, and this is because they have evolved to become bright and colorful in order to deter predators and give off a warning that's saying, hey, I'm toxic, good luck eating me, you're probably going to die. So now we're going to be going over the evolutionary identification of these frogs. The interesting part about this family of frogs is that the poison and genetic variation is very minimal among the different species. This is because they are primarily identified based on their previously stated phenotypic variations. However, this raises another issue with using physical characteristics to identify them. In the first image listed, a study was done among these three species, E. parvulus, E. bilinguus, and A. ziparo. These three species overlap in Ecuador and almost play a game of telephone with each other, where the bilinguus species mimics its more toxic neighbor, the parvulus frog, and the zapo mimics the bilinguus as it is more common in a larger span of area than the parvulus is. These species were originally thought to be close relatives, but after genetic testing was done, it revealed that these frog species are not as actually closely related as originally thought. Another interesting component to these species is that mimicry was often thought to be a way of protection from predators, so it was bizarre to see that the non-toxic Ziparo species moved toward being more brightly colored versus blending in with the background as it is not toxic. But because it was revealed that their coloration actually increases their chances of survival, it made more sense. This is not the only species that sees mimicry among other species. As more and more studies emerge, more of these imitation frogs are being uncovered. However, this is an issue for later identification indicators as we move away from phylogeny. Are there any questions?
And here's the literature from our presentation.